A very good day. My name is Lee Ming-shen. Today I'm going to explain about Reynolds transport theorem, which is RTT. Before that, in thermodynamics and solid mechanics, we often work with the system, also called the closed system. It defined as a quantity or matter of fixed identity. In the closed system, there is no mass can cross the system, but the size and shape of the system can change. In fluid dynamics, it is common to work with a control volume, also called an open system. It is defined as a region in space chosen for study. In control volume, the mass can cross the boundary. A control volume may also move and deform during a process, but many real-world applications involve fixed, non-deformable control volume. So, I'm going to take an example which is the Theorem can. One is in system, another one is in control volume. For the system, also we can consider as Lagrangian. We consider the Theorem can and its contents as a fixed closed system. The system includes everything inside the can, and as the Theorem is free, the mass of the system remains constant, which means that the mass of the Theorem that exceeds the can consider part of the system. So we can track the mass as it leaves the can. For the control volume, we focus on a fixed region or volume and analyze what has happened inside or across the boundary of the volume. The control volume could be the space around the Theorem can, or it could be the air around the nozzle where the spray is discharged. The key difference here is that we are not concerned with the Theorem that leaves the can. The focus here is the fluid that flows through the boundary of the control volume, not the contents inside the can. In fluid mechanics, it is usually more convenient to work with control volumes. So, it is a need for us to relate the change in control volume to the change in the system. So, this is what is RTT. RTT means the relation between the time range of change of an extensive property for a system and for a control volume. Okay, now we look at this figure. We got one region that consists of system and also control volume. We got one inlet and also one outlet. Okay, after that we got two times. One is t plus change of time, another is time. Then we got three different regions. One is control volume, one is system coincides with control volume, and the last one is system. Now, I'm going to explain about how this equation is going to form. Okay, before that, we look at this figure and we look at the time first. At the time, we can see that the system is perfectly coincides with the control volume, which means that the extensive properties such as mass, momentum, and also energy is shared between the system and also the control volume. While for the time plus the change of time, the system has moved along flow due to the velocity at the boundaries. We got two sections here. One is section 1, another is section 2. We also got the velocity 1 and velocity 2. Now, the extensive property B is distributed between the part remaining in the control volume, which means this area here, and also the inflow section 1 and the outflow of section 2. So these three is related. Now, the extensive property of B at two times. We talk at the time t first, which is the system equal to the control volume. So that's why this equation is formed like this. Since the system and control volume coincides, the property of the system equals the property of the control volume. While at the time plus change of time, we are going to use these equations. So, expressed in here, we can get this. Okay, why the sign here is negative? Because at the section 1, is the property loss from section 1 due to outflow, while at the section 2, is the property gained through section 2 due to inflow, which means that the fluid flow is flow from 1 to 2. So we have to minus the section 1, then plus the section 2. So we can get this equation. Okay, now we're going to find the rate of change of B system. To find the change in B system, we have to subtract the B system time from the B system time plus change of time. So this is the equations after we subtract the control volume time. After that, we have to divide the change of time to get the rate of change. So using these equations, we divide the change of time, we can get this equation. Okay. At the end, you have to using the definition of derivatives, so it will become like this. So the dB system over the dt is a change of time of B for the system, and also the dB control volume over dt is the change of time of B for control volume. As the equation state, we can know that the B out is equal to the B row velocity 1 at area 1, and the B in is equal to B row velocity 2 area 2. So this equation is also equal to this equation. The equation states that the time rate change of property B of the system is equal to the rate time of change of B of the control volume plus the net flux of B out of the control volume. This is desired relation since it relates the change of property of system to the change of the properties of control volume. So we can see that the equation implies at any instant in time where it is assumed that the system and the control volume occupy the same space at the particular. The property B in this case are easy to determine since there is only one inlet and one outlet, and the velocity are approximately normal to the surface at section 1 and section 2. Okay. However, there are several cases we got several inlets and also outlets. Okay. Also, the velocity may not be uniform. To generate the process, we consider a differential surface area, which means that we got different area here. So we got dA here on the control surface, and d0 is unit outward normal by n. We also got this outward normal acting on the different surface. Okay. Now, these equations is for the case that got several inlets and also outlets. Okay. The rho here is fluid density, and the B here is the intensive properties correspond to the extensive property. V is the velocity vector of the fluid, and n is outward pointing unit normal vector on the control surface. dA is the different area. Okay. We see that the B net is equal to B out minus B in, which means that it's equal to mass leaving the control volume minus the mass entering the control volume. Okay. The flow of property B across a surface element different area depends on the local density, the intensive property, the fluid velocity, and also the relative orientations of the velocity V and the outward normal vector n. Okay, now we are going to learn about how to determine the fluid flow, whether it is outflow, inflow, or no net flow. Referring to this figure, we can see that if the degree is smaller than 90 degree and the cos degree is greater than 0, so there is outflowing. If the degree is greater than 90 degree and the cos degree is smaller than 0, which means it's negative, so it is inflow. If the degree is equal to 90 degree, so it's no net flow. So the differential quantity is positive if the mass flowing out, and it is negative if the mass is flowing in. The properties within the control volume may vary with positions in general. In such a case, the total amount of property B within the control volume must be determined by integrations. So we can get these equations. System to control volume transformation for a fixed control volume. A fixed control volume, which means that it is not moving and also no deforming of time. So this equation is, we can substitute these equations and also these equations into this equation. So finally we can get these equations for the RTT fixed control volume. Since the control volume is not moving or deforming with time, the time derivative on the right hand side can be moved inside the integral. Since the domain of integrations does not change with time, but the time derivative in that case can be expressed as a partial derivative, since density and the quantity B may depend not only on time, but also on the positions within the control volume. Thus, an alternate form of the Reynolds transport theorem for a fixed control volume is formed as these equations. Okay. For these two cases, both of them also fixed control volume, but the difference is one is no deforming of time, another is got deforming of time. One is not alternate and another is alternate. Next, we consider yet another alternative form of the RTT equation here was derived for a fixed control volume. However, many practical systems such as turbine and propeller blades involve non-fixed control volumes. Fortunately, the equation RTT fixed control volume is also valid for moving and also deforming control volumes, provided that the absolute fluid velocity in the last term is replaced by the relative velocity. We look at the figure here. The relative velocity is crossing a control surface is found by a vector addition of the absolute velocity of the fluid and the negative of the local velocity of the control surface. So, this equation we can see that the relative velocity is equal to the absolute velocity plus the negative of the local velocity of the control surface. Okay. So, now this we can plug inside for the equation, just not the equation here. So we can get these equations for the moving or deforming control volume. Okay, just now we talked about the equations of RTT non-fixed control volume. Now we are going to talk about the alternate RTT non-fixed control volume. Okay. Note that for a control volume that moves or deforms with time, the time derivative is applied after the integrations of these equations. Okay, now I will give a simple example here for an item that is moving at a constant velocity. Okay. There is a car here moving to the right at a constant velocity, which is 10 km per hour. And also the high speed of water jet that strikes to the back of the car with the velocity of 25 km per hour. Okay. If we draw a control volume around the car, the relative velocity is VR equal to 25 minus 10, which means we will get 15 km per hour. This represents the velocity at which an observer moving with the control volume would observe the fluid crossing the control surface. In other words, the VR is the fluid velocity expressed relative to a coordinate system moving with the control volume. So finally, it can be shown that the Reynolds transport theorem for a general moving and deforming control volume is equivalent to the form given by these equations. So this is the moving or deforming, but for this is not moving. During the steady flow, the amount of the property B within the control volume remains constant in time. Therefore, the Reynolds transport theorem can reduce to this form. So the time derivative in these equations becomes 0. Okay. Note that unlike the control volume, the property B of the system may change with time during steady process. The change must be equal to the net property and transport by the mass. In most practical engineering applications of the RTT, fluid cross the boundary of the control volume at a finite number of well-defined inlets and outlets. Looking to this figure, an example control volume in which there is one well-defined inlet and also two well-defined outlets. In such case, it is convenient to cut the control surface directly across each inlet and outlet and replace the surface integral in these equations. With approximate algebraic expressions at each inlet and outlet based on the average values of fluid properties crossing the boundary. We define rho average, B average, and velocity average as the average values. This is the example of B average that across an inlet or outlet of cross-sectional area A. So, the surface integral in the RTT equation 4-44, which these equations, when applied over an inlet or outlet of cross-sectional area and then approximated by pulling property B out of the surface integral and replacing it with its average. So, from these equations, we pull the B out, then we're replacing the average properties, and finally, we will get these equations. And M instead stands for the mass flow rate. The approximations in these equations is exact when property B is uniform over cross-sectional area. So the equation just now can form to these equations. In some applications, we may wish to rewrite equation 4-47, which these equations, in terms of volume flow rate. Means that the volume flow rate we can obtain from the mass flow rate. So finally, we can get the mass flow rate equal to rho average times volume flow rate and average of the area. So, this approximation is exact when fluid density is uniform over A. So, the final equations can reduce to this. Means that here is the outlet, here is the inlet. Same goes to here is the outlet and here is the inlet. That's all for me. Thank you.